start by browsing a bit together these lecture notes, and these they are here. Give me green light if you can see a PDF file. Thanks. So this is the PDF file, and you see it's December 30th, so that's Kalle's update of the lecture notes, which is now online. And the first thing to look is the table of contents. So what is in this lecture note? There's a little introduction. It's a good read. So what are the objects of probability theory, and a couple of examples, and then discussion about probability theory and measure theory, how they are similar, how they are different things as kind of subjects of mathematics in general. Then the lecture notes have chapters, and if we look at how much there are, so there are 12 chapters. Why 12? Because we have 12 lectures to go. So there's one chapter, one lecture. And that's the rhythm of the course. And that's how we are going to go. If you look at the titles, so what we see their structure of event spaces, and let me see if I can find a pen to maybe mark a bit here. So what we have here is event spaces. Event space means sigma algebra, actually. So technically they are sigma algebras, and then that's our topic for today. Then in next lecture, we speak about what is a probability measure. We look at the really abstract definition of a measure and so on. Then we speak about random variables in the really general abstract setting. So kind of what are they as functions on a measurable space? And we learn about information related to random variables. So that's kind of the sigma algebra kind of thing for information. So how does a sigma algebra relate to information? This is kind of the basics to start, and mainly definitions, but some really fundamental important techniques and theorems as well. Then the third week, we go to independence, and we learn the independence in the really pure and abstract setting. It's also maybe close to independence in some algebraic context. For example, if you think about independence in some algebraic structures, so you might recognize some kind of really abstract fundamental connections to other types of independence there. But the main focus is applications in probability and statistics of this sigma algebra independence. And we learned something about independence in the long run, and kind of pure results about how to work with kind of fundamental long run things, so-called Kolmogorov-Zirwan law. Then we go to the next week, and we switch a little bit focus. So we do an integration theorem. So calculating probabilities is actually integration, nothing else. So calculating probabilities, calculating expectations, calculating predictions, filtering, all of this is kind of fundamentally integration. It's integration of something, and this is why we will need to spend a bit of time to kind of learn the really precise and abstract way of thinking about integrals and integration. And this content is quite similar to the course in measure and integral. So what does an integral mean? There are actually a few different definitions of integrals, but there's one which is the standard one, and that is called the Lebesgue integral. So this week is actually devoted to learning how to kind of define and understand what a Lebesgue integral is and how to calculate with that. Actually, the calculations are usually the standard thing. So the integral of x is 1/2 x squared, and the usual thing that we know. So for ordinary things, the Lebesgue integral is the same as what we learned in high school. but but what is different is that Lebesgue integral has nothing to do with the Lebesgue measure as such. So they are different things, and that becomes hopefully clear when we proceed. Then we look at expected values, which are just some sort of integrals written in a certain way. And the very important part of the course is the product spaces and how to work on probabilities in product spaces, joint distributions, product measures, densities on product spaces, and so on, and kernels. And then final week, we go to the stochastic convergence. So what does it mean to be close to something for random elements on in the probabilistic sense? There are different definitions, and we look at some of the most important of these definitions, so-called weak convergence, strong convergence, and convergence in probability. And we finish with central limit theorem, the proof of that, and what does it precisely say and what not. That's about the contents. What else is there? There are appendices. So there's Appendix A. What does Appendix A say? It says about set theory and numbers. So you could check about this maybe right during the first week and see if you need something of that, or if that looks familiar, or if not. Something about topology, or kind of the key things from the course, metric spaces, the Euclidean spaces course. So the key things in the nutshell. These are important appendices. What else is there? There are some other appendices. So C is about Dinghin's identification. So these are proofs of some of the technical theorems. So maybe they are put to the appendix because maybe not each of you wants to read them in the first place. But I know that some of you want to kind of know that how everything is proved, and how everything is proved is kind of Kalle has tried to work hard on making this lecture note as self-consistent as possible. So for everything, there should be a proof available, whatever is stated, starting from the fundamental axioms. And kind of four proofs are here: Appendix C, D, and E, and then there's Appendix F. And finally, there's maybe some material. So there's a description of the notation. So for example, let's see. This is the way to denote the non-negative integers. It changes in different lecture notes. Here is this one. N is now the natural number starting from 1, and so on. And then these are the intervals, logical notations, blah, blah, blah. And then there's set theory notation. This is important. So what is the power set? It's the collection of all sets. P for power. So that's the power set. And it's defined in this way. The power set of some set S is the collection of all subsets of S. Right. Okay. And maybe in the end, there's also an index so you can browse with different topics. References: the book of Williams, the book of Jacob and Proto. These are the books. And then Duretz has also a book on probability theory. And then you can also browse the Juha Kinnunen's lecture notes about measure and integral if you want to see how the analysis point of view to the measure and integral is done. In total, this is 174 pages, which is quite but bunch of reading for 6 weeks. Luckily, we don't need to read everything. So in the kind of best case scenario, so you might be familiar with the appendices already, or the kind of the appendices A and B, and then you don't need to read the rest of the appendices if you want to learn fast. So this 126 pages should be about sufficient for the course. So that means 10 pages per lecture, 20 pages per week. So that's about the amount of reading for this course. Right, this was kind of the little browsing of the contents. Are there some questions that you might like to bring up about the contents of the course? Okay, maybe then let's have a look at the chapter O or chapter 0. That's maybe Roman for 0, introduction. And let's go there and let's browse a bit. There's a foreword. You should read it. So let's see. This is the introduction. Give me green light if this is well visible for you. Now we will look at a little bit of the details. So yes, thank you. So that's the introduction. So what are the basic objects of probability theory? We start about this. So we use omega to denote kind of fundamental abstract space of outcomes. So they are called outcomes or realizations or samples. So all these three things refer to some abstract points in omega, which is some set that what we might not always specify. The kind of stochastic style of writing and reading and speaking is that we don't tell what omega is concretely unless it's needed. Sometimes we need to do it. And it's kind of related to the magical sampling of randomness, this omega, that we pick one outcome, little omega, that describes how the world looks. Then what are events? So events are actually sets. So thing is that an event is a set. So that's what we have learned already in basic probability, the idea that events are sets. And that's what we are going to do precisely and exactly and rigorously during this course. So an event is a subset of omega, and but we need to restrict a bit. So we need to restrict a bit. Not every subset of omega can be an event in general, but we'll learn about this. So we need a good collection of events. And then finally, there's the measure probability, which is a function from this calligraphic f to the real numbers. So we assign to each event a number p of e. That's the probability of the event. It's a number between 0 and 1, including 0 and including 1. And then we work with random variables. So random variables in abstract sense are functions from the space of samples, the sample space omega, to some space S of realizations. So it doesn't need to be real numbers. It could be a set of letters, for example, if we are doing gene modeling. So this could be a set of 4 letters. It could be zeros and ones if we are doing information theory. That's how we often look at this. It could be sequences of zeros and ones. It could be a sequence of numbers when we work of stochastic processes, and so on. It could be a set of graphs if we work on random graphs, and that's how it goes. The expected value is an integral, and that we will learn about the Lebesgue integration theory. And we will eventually write the expected value of x as an integral over this abstract space omega with some measure, and we will learn what this means precisely. When this is a general measure, maybe it has a density, maybe not. Right. Then, okay, the basic example, maybe we will do a couple of examples next.
A question.
Please.
A question on the events, and
Yes.
when an event is realized, so the small omega belongs to the subset E. So all of the elements of E do not have to be realized for the event to be realized.
Yes, that's correct.
Okay.
Yeah. Other questions? We will come back to that, and when we work with homeworks, this becomes clear. Let's look at a couple of examples before we have a little break, maybe. So the basic example, the really basic examples of all probability is the coin toss or coin flip. So we pick up one coin, we flip it and see if we get heads or tails. This is very elementary, and you might wonder why are we doing this in the advanced course, but we want to do it to see how the really elementary things can be kind of seen in the abstract framework. So in the abstract framework, how we see it is that we have heads or tails, so there are two possible outcomes. Then omega is a finite space of two elements in this way. And the sigma algebra, or no, yes, as events, so we don't yet define what the sigma algebra is, but we say that the space of events will be actually defined as the set collection where we have the empty set, we have the set with one element, and H, and set with one element T, and then the set with two elements H and T. And why do we need to have all of these four things? The empty set is representing the fact that nothing happens. It's irrelevant in some way, but it's always included so that the probability of nothing happens is zero. And this full set is representing the fact that something happens. So either we get heads or tails, and then that probability should be one. And that's how the coin flipping goes. And in this case, we actually note that. Let me try if I can make annotation using the zoom window. Let's see if I click draw here. I'm sorry about this. I'm a little bit still learning with this technology. So yes, what I wanted to do. In this case, F is actually is a set of all subsets of omega. If you look at this, omega is a set with two elements. If you think about the set of all subsets of omega, then what are those? So those are the set of this element, the set of that element, the set of nothing, and set of everything. So these four elements constitute the set of all subsets of omega, and this has a special name. It is called the power set of omega. And it's denoted in Kytölä's lecture notes as P of omega. And in this case, when we have a finite set of samples, when omega is finite, we will always use the power set as the fundamental collection of events. And in that case, we don't know any measure theory or any sigma algebras or any technicality. So in practice, for finite spaces, we don't need any advanced courses and advanced techniques. But the trip from finite spaces to big spaces is not long. So let's go to the next example. So let me clear this little note. And we go to the next example, which is think that, okay, what if we make several coin flips? Not one, not two coin flips, but maybe some number of coin flips that we don't fix a priori. In that case, in principle, there could be an infinite amount of coin flips. If we want to kind of model a system or situation where we don't fix, there will be more and more coin flips over time, and we want to do, for example, adaptive Bayesian filtering. So we want to kind of understand what happens when time goes on and on and on, and we continue this coin flipping or continue observing some discrete signal or continue doing a coin flip. So remember, coin flip is actually a thing that represents some randomness. It's a binary thing, but we speak about coins, but the coin is actually representing a really general thing. So if you think about repeated coin tossing, so things become already something where we don't anymore, where we cannot anymore to work with the power sets and finite spaces. So this space is now, the sample space is um, the set of infinite sequences. So omega is an infinite sequence. So for example, first we do heads, then we get tails, then maybe tails, tails, heads, tails, and this is an infinite sequence of outcomes. So it continues, and one of this type of infinite sequence is one omega, one little omega, and this set of infinite sequences is denoted by the set to the power n. So it means all maps from n to the values h and t. So we could think that, okay, omega of 1 is equal to h, omega of 2 is equal to t because that second was t, omega of 3 is equal to t because the third outcomes from was t for tails, and so on. So we can also write omega is a sequence of omega 1, omega 2, omega 3. We number these members of this sequence omega in this way. Okay, and now we see that omega is list. It's an ordered list of elements. So omega 1, omega 2, omega 3, and so on. And what it means is that we can also interpret it that omega is a function, that it maps I, which is a number, to the value of in this position I, that's omega I. So you can think that omega is a function. And in that case, omega is a function from n, so I belongs to n, the index, and then this index is mapped to the value of omega, omega I, you see, in this way. So we are looking at the space of functions from the natural numbers to the coin flip outcomes h and t. And what about this space? Is it big or small? Well, obviously every member is an infinite sequence, so obviously there are infinite amount of members also in this space omega. So this is sometimes we use this for the number of elements, sometimes we use this way. Regardless, this is infinite, so we know that omega has infinitely many members. But what more? The key important thing is that this is uncountably infinite. So omega is actually, in this case, the repeated coin tossing, it's an uncountably infinite set. And what is countable and uncountable? So that's something that is nicely discussed in Appendix A, so you can go there and browse. Okay, so to define events and probabilities, now we are working in uncountable spaces, and we need to be really, really careful to work with this. Are there questions about
Sorry.
this notion? Please.
Um, I have a feeling like this is a countable infinite set
Yes,
because they
it
are
feels
discrete.
countably infinite. Yes, it feels that it should be countably infinite because we have something here finite and something here n is, this is countably infinite, this index set. Finite and countably infinite. But then we take this product space of kind of a countably infinite product of finite space. It feels countable, but it's not. Why is it not? Think about replacing h and d by zeros and ones. So what does that become then? We are looking at all sequences of zeros and ones, for example. This is one sequence, and one sequence could be the set of all zeros. One sequence could be the sequence of all ones. Now think about mapping these binary sequences to real numbers. Think about that this all zeros is actually the number which is in binary representation the 0.0000, and this is let's say 0.11111 in the basis 2 binary sequence representation. So actually then every sequence corresponds to one real number between 0 and 1. How many real numbers do we have between 0 and 1? This set is uncountably infinite. So that's why actually, although this space omega, it feels and looks countable, it smells countable, but it's not countable. It's uncountably infinite. Okay, I hope it answers this question.
Yeah, thanks.
Okay, very good question actually. Really, really good point to make. Thanks for this. So this is about the repeated coin tossing, that it seems that, okay, finite thing. We don't need any abstract things, but actually we do. So to understand probabilities here, we need to have a good definition of probabilities and measures and events in uncountably infinite spaces. We could ask, okay, if xn denotes the relative frequency of heads, for example, here, so that's how we could write it. It's the function that maps an infinite sequence omega to the number. We count how many j's are up to among the first n, which result in heads, and then we divide by n. So this is the fraction of heads in the first n coin flips. And this is kind of a map from this big omega to real numbers. And this is what would be a random variable. And we could ask, does this sequence of random variables, does it converge in some sense? And it's clear that it cannot converge with probability 1. So for some omega, this thing does not converge, but then identifying when things converge and when not. So that's one of the goals of the course. And then we could ask, for example, this sense of convergence, that the fraction of heads among the first n coin flips, intuitively, we expect that it should be close to 1/2. In the long run, 1/2 the coin should be heads, 1/2 of the coin should be tails, intuitively so. So intuitively, the difference from 1/2 should be close to 0. What does it mean to be close to 0 for large n? This is one way of saying it. The difference from 1/2, the probability of that being bigger than any epsilon should go to 0. The probability of that is n goes to infinity. But how to define, what is P? How to define B rigorously and axiomatically? What is this P? So that's why we need, even for this repeated coin tossing innocent thing, that's why we need to work with uncountable spaces. There's another example here related to Galton-Watson processes. Let's skip it for now, but if you want, you can read it. It's a nice story about Galton and Watson branching processes. Similar things, but yes, during the lectures, we don't have time to discuss everything here. Finally, there was the discussion about probability and measure theory, so please have a read of this. It's a nice bedtime story to check. Okay.